Hello everyone, I am Professor Sukruti Joshi from Department of Applied Science Chemistry at Brønsted University, Ahmedabad. Today we are going to learn about acid and base. Now before we are taking introduction that what is an acid or what is an base, we have to know which are the properties of their acids and their bases. So here the properties of acids and bases are given. Acids turn blue litmus paper into red, they taste sour. Acid corrode metals, or you can say acids can corrode anything in the world. Positively, they are basically positively charged hydrogen ions. You can represent it by H plus ions. Now the properties of bases, they turn red litmus paper into blue, that is bitter. Negatively, they are basically negatively charged hydroxide ions. You can say they are OH minus ions. They feel slippery. Most hand soaps and drain cleaners are bases, and strong bases are caustic. Now from this you can see that acids are corrode anything and bases are caustic to each and everything. So you can differentiate by this. Now what are acids? So in the pH range from 0 to 6 it is acid. That range defines you what is an acid, and from 14 till 14, from 8 to 14 it defines you base. So what is a base? From pH, the compound which has pH from 8 to 14 is known as bases. So in this way we can differentiate. Now there are three concepts are there which are produced to explain what are acids and what are base, or you can say that they are given us the definitions that what are acids and what are base according to their own theories and according to their own concepts. Now here there are basically three concepts: Arrhenius concept, Lowry-Brønsted concept and Lewis concept. These three concepts has been developed by different scientists to explain what are acids and what are bases. From that, the first one is Arrhenius concept of acid and bases. According to Arrhenius concept of acid and base, an acid is a substance that when dissolved in the water it increases concentration of H plus ions, or you can say hydronium ions, H3O plus. Now as we know that chemists often use the notation H plus for the H3O plus ion, or you can say we are using H3O plus for H plus ions and call it as the hydrogen ion. Both are the same. H3O plus is known as hydronium ion while H plus is known as hydrogen ion, but both are the same thing. Why? Because remember that however that the aqueous hydrogen ion is actually chemically bonded to water, and that is H3O plus. Now as we know that hydrogen ions or any other ions cannot be there in the free form in any other solution. So here H plus ions that are free in form, they bind with the H2O and they form H3O plus. Therefore we are right here H3O plus rather than that of H plus. Now according to Arrhenius concept of acids and base, an acid is a substance that when dissolved in the water it increases concentration of hydronium ion, or you can say hydrogen ion. So it is just represented here that how the H plus ions is bonded to another H2O plus and they form H3O plus. The structure of that thing has been shown here. Same thing will be here written. Now according to Arrhenius concept of acid and base, what is a base? A base in the Arrhenius concept is a substance that when dissolved in the water it increases concentration of hydroxide ion, or you can say OH minus ion. Here in the Arrhenius concept, a strong acid. Now in the Arrhenius concept, the concept it also defines that what is a strong acid, what is a strong base, what is weak acid, weak base, and also conjugate acid and conjugate base. So firstly, in the Arrhenius concept, a strong acid is a substance that ionizes completely in aqueous solution to give H3O plus and an ion. Now we are taking an example of perchloric acid, that is HClO4. When HClO4 is dissolved in water, it gives us H3O plus ClO4 minus. Here you can see that HClO4 completely ionizes into H3O plus ClO4 minus. It itself ionizes completely, therefore it is known as strong acid. Another examples of strong acids are HCl, HBr, HI, HNO3 and H2SO4. As we know that HCl is hydrochloric acid, HBr hydrogen bromide, HI hydrogen iodide, HNO3 nitric acid and H2SO4 that is your sulfuric acid. All are the strong acids. Now what is a strong base? In the Arrhenius concept, a strong base is a substance that ionizes completely in aqueous solution to give OH minus ions and cation both. Here an example of NaOH, that is sodium hydroxide, is given. Here you can see that NaOH when dissolved in H2, it gives you Na plus OH minus. Here itself ionized completely into OH minus, therefore it is known as strong base. Another examples of strong bases include LiOH, KOH, CaOH twice, SROH twice and BOH twice. Here LiOH is lithium hydroxide, KOH is potassium hydroxide, CaOH twice, calcium hydroxide, SROH twice, strontium hydroxide and BOH twice. That is your barium hydroxide. Now most other acids and bases that you can encounter are weak and they are not completely ionized and exist in reversible reaction with the corresponding ions. You can see that we are taking an example of acetic acid, that is C2H3O2. Here when it is dissolved in water, it gives us H3O plus C2H3O2 minus. Here you can see that they both combine together or they both react together to give again acetic acid and water. Now they both combine together to give H3O plus C2H3O2 minus. Again this both combine or react with each other to give this thing. So they are not completely ionized, therefore they are known as weak acids or weak bases. Most other, now another example is given, that is ammonium hydroxide NH4OH. It is a weak base. You can see that NH4OH is converted into NH4 plus OH minus. Both this combine together, NH4 plus OH minus combines together to give NH4OH. Again NH4OH ionize itself into NH4 plus OH minus, and again the same cycle will be repeated for longer times. Now there are certain limitations of any of the concepts so that the new concepts can arrive. Here the limitations of Arrhenius concepts are there, so that Lowry-Bronsted concept and Lewis concepts come into existence. You can see that the limitations of Arrhenius concept, why we need to invent another concepts of acids and bases, why Lowry-Bronsted concept and why Lewis concept has to come into existence. The reasons are given here, or you can say the limitations of Arrhenius concepts are given here. The Arrhenius concept is limited in that it looks at the acids and bases in aqueous solutions only. It can explain us any of the property of acid and base only when the compound is dissolved in water. If the compound is dissolved in any other solvent, it cannot explain us the concept of acid and base. This is the first and the main limitation of your Arrhenius concept of acid and base. Second one, in addition, it singles out the OH minus ions as the source of base character when other species can play a similar role. It is here explained that OH minus contained compounds only known as base, but another compounds are also there which can act as a base, but that doesn't contain OH minus ion in there, but they known as bases and they behave as bases. So that thing is not explained here. This is another limitation of Arrhenius concept. Third one, broader definitions of acid and bases are discussed in the next sessions. Therefore, due to these limitations, we have to invent another concepts of acid and base. Next concept is Brønsted-Lowry concept of acid and base, or you can say Lowry-Bronsted concepts of acid and base. Now, according to Brønsted-Lowry concept, an acid is the species donating the proton in proton transfer reaction. In the above reaction, or you can say in the above concept, Arrhenius concept, we have studied that when a compound is dissolved in water, at that time if it produces or increases concentration of H plus ions, then it is known as acid. If it increases concentration of OH minus ion, then it is known as base. Here another concept comes which deals with proton transfer reaction. So here, according to Lowry-Bronsted concept of acid and base, an acid is a species which donates the proton in proton transfer reaction, and a base is the species which accepts proton in the proton transfer reaction. That compound, or you can say that species, is known as base, while here which donates is known as acid. In any reversible acid-base reaction, both forward and reverse reactions involve proton transfer. As we know that in every reaction there is a proton transfer happens, and according to that only here this concept can be applicable on each and every reaction. Now we are taking an example of a reaction between NH3 and H2O. So when NH3 and H2O reacts with each other, they form NH4 plus OH minus. Here H2O has, as we know that H2O has two ions, H plus and OH minus. So from here the H plus will be transferred to NH3. NH3 will be accepting that proton while H2O is donating that proton. Therefore H2O becomes Lowry-Bronsted acid and NH3 becomes Lowry-Bronsted base, and they form NH4 plus OH minus. Now in this reaction, as this reaction is a reversible reaction, here what happens, NH4 plus has already one extra hydrogen ion, so it donates it to OH minus ion to form H2O. So NH4 plus donates its hydrogen ion to OH minus ion, therefore this is donating, so it becomes acid, while OH minus is accepted the proton, therefore that is known as base, Lowry-Bronsted base. Here you can see the hydrogen ion transfer, and again this both reacts with each other to give you NH3 and H2O. Now the cycle runs again and again, the reaction will continue for longer time. Now in the reverse reaction, same thing will be returned here. Again the species NH4 plus and NH3 are conjugate acid and base pair. Now the next concept which comes is conjugate acid and base. Now what are conjugate acids and what are conjugate base? Here you can see that in this side NH3 acts as an acid, as a base, and NH4 plus acts as an acid. So from NH3 to NH4 plus, in that side it behaves as a base, in this side it behaves as an acid. So these two things are known as conjugate acid base pair. The species NH4 plus and NH3 are conjugate acid and base pair. Basically a conjugate acid base pair consists of two species in an acid base reaction, one acid and one base that differ by the loss or gain of a proton. Here we can see that one loses proton while another gains proton. So here this is NH3. You can see that here NH4 plus is the conjugate acid of NH3 and NH3 is the conjugate base of NH4 plus. Same thing will be written here. Your NH4 plus is the conjugate acid of NH3 and NH3 is the conjugate base of NH4 plus. The Lowry-Bronsted or the Bronsted-Lowry concept defines a species as an acid or as an base according to its function in the proton transfer reaction. As we know that it gives us the thing or the species which donates proton is known as acid, while the species which accepts proton from any other substance or any other compound is known as Lowry-Bronsted base. Now another concept was also there, that some of the species can act as both acid and base also. So here that species is known as amphoteric species, or you can say amphoteric substances. An amphoteric species is a species that can act either as an acid or a base. That means that it can gain an electron, or you can say it can lose a proton, right? Again, gain a proton and lose a proton. For an example, we are considered one example between HCO3 minus and OH minus. Here HCO3 minus acts as a proton donor and in the presence of OH minus. So which species can donate is known as Lowry-Bronsted acid. Therefore your H3O3 minus becomes an acid while OH minus becomes a base. Here it donated its proton to OH minus ion. Therefore this is known as Lowry-Bronsted acid while this is known as Lowry-Bronsted base. It gives you CO3 2 minus plus H2O. The same situation happens. Now how can we prove that in one time it can act as acid and another time it can act as a base? So here the thing is written like when HCO3 minus is reacting with HF, that is your hydrogen fluoride. Here what happened? The HF, the hydrogen ion of the HF will donate it to HCO3 minus. So this becomes acid, Lowry Bronsted acid, while this becomes Lowry Bronsted base. You can see it there, and that forms you H2CO3 plus F minus. So here you can see that HCO3 minus in one reaction acts as an acid, while in another reaction it acts as a base. Therefore it is known as amphoteric substance. Now another example of amphoteric substance is water. Now here we can see the amphoteric characteristic of water, because it is very important as it can play as an universal solvent for any of the compounds. Therefore it gives us very important thing for that. Water reacts as an acid with the base NH3. Now when NH3 reacts with H2O or H2O reacts with NH3, what happened? As we know that H2O has H plus and OH minus 2 ions, so it donates its H plus to NH3. So this becomes the Lowry Bronsted acid, while that becomes the Lowry Bronsted base, and it gives you NH4 plus OH minus. Now same thing, when H2O reacts with HF, what happened? HF donates its hydrogen ion to H2O, and that becomes Lowry Bronsted acid, while your H2O, which is accepting the proton, it becomes Lowry Bronsted base. So here, and that forms you F minus plus H2O plus. Now here you can see that here it behaves as a base, while in above reaction it behaves as an acid. Therefore you can see that water can be acts as acid also, and water can be acts as a base also. That means that it can lose a proton also, and it can gain a proton also. Next concept is Lewis concept of acids and bases. Now here the another third concept come across, that is your electron pair. Now the according to Lewis concept, what is an acid? Electron pair acceptor species or electron pair acceptor compound is known as Lowry Bronsted acid, while electron pair donor compound is known as Lowry Bronsted base. Here we are taking an example, that is when A plus plus B minus reacts with each other to give A to B, that gives you A and B. Here you can see that this has higher electrons, or you can say this has extra electrons and this has lesser electrons. So from here to here the electrons will be moved. Now this is donating, therefore it becomes Lewis base, while this is accepting, electron acceptor, that means it becomes Lewis acid. And finally you are getting your AB, which has coordinate covalent bond. Now here the reaction is given, BF3 plus NH3 gives BF3, the whole compound will be formed. Here you can see that NH3 has extra pair of electron, while BF3 doesn't have any extra pair of electron. So this electron will be moved from NH3 to BF3, and that gives you the whole compound. Now the next topic is the pH of the solution. What is the pH of solution? Now although we quantitatively describe the acidity of a solution by its H plus, or you can say hydrogen ion concentration, it is often more convenient to give acidity in terms of pH. How can we define pH? The pH of the solution is defined as the negative logarithm of the molar hydrogen ion concentration. The pH is represented by pH is equal to minus log of H plus. This gives you the concentration of H plus ions. Now we are taking one example where the hydrogen ion concentration is given to you. The hydrogen ion concentration is 1.0 into 10 raised to minus 23. So when we are putting this value into its equation, pH is equal to minus log of 1.0 into 10 raised to minus 3, that the answer will be 3.0. So your solution has the pH 3. It is acidic in nature. In a neutral solution whose hydrogen ion concentration is 1.0 into 10 raised to minus 7, the pH is 7. As we all know that for acidic solutions, the hydrogen ion concentration is greater than 1.0 into 10 raised to minus 7, and the pH is less than 7. They are behaving as acids. In basic solutions, they are above 7, greater than 7, you can say from 7 to 14. Now here a pH scale is given to you, which shows different examples and the whole pH range, that from where to where it really exists. Here you can see that from 0 to 14 in your scale, 0 to 6, from 0 to 6 it is acid, 7, this portion is a neutral portion, and from 8 to 14 it is actually a basic portion. Here some of the examples are given. The highest or the strongest acid is HCl. It is a 1 molar HCl, and here the highest, or you can say the strongest base, was your NaOH, 1 molar NaOH, which has the pH of 14, while here HCl has the pH 0. It is the strongest acid. And the example of neutrals are blood, water, whatever you are taking. Another example, now we are taking one example of pH. A sample of orange juice has a hydrogen ion concentration of 2.9 × 10⁻⁴ molar. What is the pH of that? Here, as we know that the equation pH is equal to minus log of H plus. So pH is equal to minus log. We are putting this value into this 2.9 × 10⁻⁴, and we are getting the result is 3.54. Thank you.